All right, John.
All right. So welcome, everyone. Good morning. Thank you for tuning in. I want to welcome Dr. Sean Lin from UCLA to our Grand Rounds this morning. This is quite a special day in the sense that he is a new father with a 5-month-old, which is the only reason why being up here at 4:30 in the morning his time seemed like a reasonable thing to do. I confess he's probably ruining the day he met me at AAO 2019 and actually answered my email about being our visiting professor today, but I'm very excited to have him. His talk at that meeting really impressed me, and I think he will be even more interesting to all of you today. So he is the Associate Program Director at UCLA and also Assistant Professor in the Division of Cataract and Refractive Surgery. And he's also the Medical Director at the UCLA Calabasas Stein Eye Center. He did medical school at Stanford, his residency at UCLA Stein Eye Institute, and he was a 2018 recipient of the Heed Fellowship and the Abelson Fellowship, and completed his Cornea, Cataract, and Refractive Surgery Fellowship at Mass Eye and Ear. He has a strong interest in ophthalmic education, and if you doubt that, consider that he's here in his office at 4:30 in the morning to talk to us. So I think it's pretty clear that he is very keen on education. And he's also founded iGuru, an educational platform which has been visited more than 1 million times a year by other ophthalmologists from over 125 countries around the world. So his research is focused on combining human and machine intelligence to deliver exceptional surgical results to his patients, and hopefully ours too. So welcome, Dr. Lin.
As many of you who are new parents, I'm really just trying to escape my baby for a couple hours. So that's why I'm here, but thank you. So let me go ahead and share my screen. I think the host needs to allow me to do this.
Try it now.
Okay, now we're good. So let me go ahead and share screen number 2 and start my presentation. You should be seeing some slides now.
Mm-hmm.
Okay, wonderful. So my talk's title today is MD's Role in AI World. And this is kind of an expansion of a talk I gave at AO that Dr. Lloyd was at. And so I actually wanted to start by telling you a little bit of a story about some bad intelligence and serendipity. So 4 years ago, as you recall, or may not recall, cryptocurrency was super hot. So this story happened in kind of mid-2017 to early 2018. So at that time, I was a third-year resident at UCLA. And if you recall from cryptocurrency, the way you obtain cryptocurrency is by, quote, mining it, which is essentially using a very fast computer to decrypt strong cryptographic formulas. So in mid-2017, I was in LA. Like anyone living in LA, I was looking for a side gig. And so I thought it'd be fun to learn and play in cryptocurrency. And so by my calculations, I could make about $1,000 a month while investing about $50 worth of electricity. And so that seemed pretty good, and why not? So I built this cryptocurrency mining rig and I set it up in my room. And the problem with it was the middle of the summer in LA, and it was very loud and very hot, and my wife wasn't a very big fan of it. So I actually ended up storing it in the attic of my apartment, running power cables with the walls. Definitely not up to code, but I enjoyed learning about the process. So then fast forward a couple of months, I'd been mining cryptocurrency for a while, and Ripple was a cryptocurrency that was around 25 cents, and I thought they had a good mission. And so I decided to invest a few $1,000s in it. Has anyone bought cryptocurrency in the early days? Okay, so this will be interesting, hopefully. So I bought 30,000 shares at 25 cents. And when you buy cryptocurrency, especially in the early days, it is a crazy process. It's really scary. You create this account, which is just a bunch of random numbers and letters that comes with a private key. Then you have to wire money to these exchanges, and then they convert the money into the crypto that you want, and then they send it to your account. If you screw up a digit and you put it in someone else's account, there's no do-over. The money is gone. If you forget your private key, the money is gone. If you get mugged and your cell phone gets stolen and a thief takes your key, your money is gone. And every few weeks in the early days, you would hear about these exchanges getting robbed, quote, robbed, which may or may not be the founders just walking away with some of the money. So when you buy the crypto, you never leave it in exchange. You just use the exchange to buy it. Then you move it off into a paper wallet, quote, which is literally just a piece of paper with 2 numbers on it. One is your account number, one is your key. And then the people who have a lot of crypto, they actually take the paper wallet and they just put a portion of it in different vaults around the world. So you can see that this is kind of a scary process. And this, I think, is the biggest problem with cryptocurrency, that the average person would not go to the trouble of doing this. And sending money around is actually a very, very scary process, and there's no safeguards. So anyway, so to go on with the story, I put the money in crypto, and this crazy thing happened. Around mid-December, everyone suddenly decided that crypto was the best thing ever, and then the institutional investors start buying it. So then there was this insane rocket ship where the crypto essentially could not be purchased fast enough. It was like the tulip boom. A lot of people compared it to in Holland. And there are arbitrage opportunities. You can buy it and sell at the same time and make money. So I just hung on to my little share of it. And eventually it was about $3.84. And I thought, oh my God, I'm a resident. I could probably buy a Tesla now. But, as you know, the boom definitely died. And I wish I could tell you that I sold it right there, or even here. That would be nice. But in actuality, it was pretty close to here. And so I ended up with my Prius, which I'm still driving. And more importantly to this story, I had a very, very fast computer. So this is the underpinnings of why I had this extremely fast computer to do deep learning. So then I tried to repurpose this computer to do what I'm going to tell you about today. So let me tell you what I'll be going over. We'll be talking about artificial intelligence, how I became interested in AI, and then talk about why now, how to learn AI, which is a conversation I had with Austin about a year ago, building an AI lens power formula, talk about the EyeData initiative, and then I want to switch gears and hopefully offer some thoughts on human intelligence, talk about iGuru, and then finally end with talking about what I think our role as MDs are in the AI world, and kind of talk about some frameworks that guide my thinking when I'm thinking about research in AI. So we'll start with this. So I was born in Shanghai, immigrated to the US at age 4. And in high school, I worked at Best Buy. I was one of the, I don't know if you guys have Best Buys, but there's a group of people called Geek Squad members who sit behind the tech bench, and then we fix computers. So I was part of that. And in high school, I wrote a paper about AI. This was in 2002, and I wrote about evolutionary programming. I'm going to take this off because it's very embarrassing. So then I went to college. I went to med school. I did an MBA at the same time. I did residency at UCLA and then did my fellowship in Cornell MSI. So I won't belabor this, but there are a ton of papers now in AI, and this hasn't even been updated for the last 2 years, but I'm the millionth person to tell you that AI is super hot. So I propose that it's a combination of 3 things: techniques plus computational power plus data. So let's talk about techniques first. So in the beginning, so let's talk 1994, this red band on the bottom represents neural networks. And you can see that it represents a small part of the landscape of artificial intelligence at that time. But something really interesting happens in 2012, and you can see there's a huge boom. That red band expands to be the majority of the AI landscape, right there. And one of the things that happened around this time was a competition called ImageNet. This is a competition where computers or teams compete to write algorithms in order to identify images from a large data set of millions of images. So they're given the data set, they're instructed to write the algorithm, and then they're asked to, and then the algorithm is tested, and then they try to achieve some kind of percentage of accuracy. So if you look at the ImageNet classes, there are easier things like these, stingrays, porcupines, stuff that are pretty straightforward given enough things. But then there are really hard things like this. I don't know if I could tell you the majority of what these things are if I didn't have the labels on them, but here's what they are. So these are actually fairly difficult images. And so the goal is to get as high as possible. So this is the interesting thing that happened in the ImageNet competition. So here's humans at around 95%. These humans are much smarter than me because I'm not sure I could do 95% on these images. But you can see that around 2012, there's quite the spread of results. Each dot here represents a team that is doing deep learning. So 2011, it gets a little bit tighter. Techniques are getting better, but no one's broken 75%. 2012, remember that year I talked about, is when the first team breaks 75%, and it doesn't just barely break 75%, they crush it, 85%. Does anyone know where this team came from? Austin maybe knows. University of Toronto. This was the first team that cracked 75% on ImageNet, and they won the competition that year. And they're widely credited with kind of starting the boom in deep learning because of their technique. And then of course, the next year, everyone followed them. So everyone did better. 2014, everyone did better still. And by 2015, the best algorithm had achieved and surpassed the performance of human beings. And so they stopped running the competition because there was no point at that point. So secondly, computational power. In 2019, I could build a PC like this for around $3,500, and we'll call that 1x speed. In 2021, not only is it a lot cheaper to build a PC like this, one GPU, a graphics processing unit, is about 10th the cost, but it's around 10,000 times the speed. This is way faster or greater than Moore's law. And that's because these graphics processing units are just made to do floating point calculations, which are the basis of deep learning. But here's where it gets really crazy. So Amazon had billions and billions of dollars in revenue. If you look at where their revenue came from, it wasn't necessarily from the Amazon where we buy things, but it's from the Amazon where people pay money to host products on the cloud, on their computing platforms. So you can rent a computing platform from Amazon. So you can rent something like this. They call this P3DN 24 extra large. And you can see that this is a pretty fast computer if you know computers. And I kind of priced this out on Amazon, and it costs $117,000 to create this computer. But the shocking thing is that you can rent this computer for $31 an hour. So let's go back to our math. To do a calculation on that PC from 2019 is 1 year. If we did it in 2021, it would only take an hour at 10,000x of speed. And if we did this calculation on one of these computers that you can rent from Amazon, we're talking a million x of speed, it's really only $31. But in fact, it's not $31 because it's so much faster. It only takes 32 seconds to run that calculation. So now we're talking 31 times 32, we're talking 52 cents. So that's why I propose that computational power is a huge component to what's driven this boom. And we'll say lastly that data has also been huge. I won't belabor this. Every single minute, there's tons and tons of data that we're just supplying to the algorithms, and not just social data, but healthcare data. We're just generating this at unprecedented rates. So it's the combination of these things, techniques plus computational power plus data. So then how do we learn how to do AI? You can go online actually, and you can take a course from MIT for $3,200 that proposes to teach you AI so that you can function as a data scientist or as a machine learning scientist. You could also take a course from a place called Springboard. And finally, there's this website called Expertfi. For $13,000, they will teach you how to do AI programming, but they do have a money-back guarantee. And they say that of 1,400 students enrolled, 0 have asked for refunds. So that probably points to a pretty healthy job market for a machine learning engineer. But because I was a resident, I didn't have this amount of money to invest. I went to a website called DataCamp, which is $29 a month. And the beautiful thing about DataCamp is that there's a couple, once you subscribe at $29 a month, you can take any of hundreds of classes on machine learning, on data structures, and you really only need a couple of these classes to go from zero knowledge in machine learning and a strong desire to not huge knowledge in machine learning, but some knowledge enough to be able to put together something. Now, of course, these formulas that I'm putting together, I'm writing, are not going to be as good as the ones that are put together by somebody who's been working in this field for a long time. But as I'll talk about later, I think that we have a role in teaching ourselves the basics of machine learning so that we can interface with these kind of engineers down the road. So I'll talk about that later. So let me tell you kind of how I went around building this AI lens power formula. So in AI, there's this concept called ground truth, which is the gold standard truth, which an algorithm is trying to match, or what you're trying to match. So for example, if I ask you this question, what is this animal? It's pretty obvious. The ImageNet algorithms of 2010 would obviously be able to figure out what this is. But if we ask the question, is this glaucoma? This is not so obvious. And even if you ask a panel of experts, they may disagree. So you want to find a research topic, ideally, that has a very strong ground truth, meaning we have a very high certainty as to what the true outcome is. So this is why I picked intraocular lens power as a starting bed for this, because we have the preoperative biometry, we have a known lens power, and we have a fantastic ground truth. We have the postoperative MRX. So I took a billing database using, in the United States, the CPT code is this one. And I looked at biometry data, operative nodes, postoperative data, and then looked at surgeon aim. But I realized later on surgeon aim wasn't that important. It's really more about what the biometry looks like and then what was actually achieved. So I put this into a compiled data set. And so I found 9,185 records in the billing database. And then I thought about how to process these records. So if I were to look through each one, each chart, it would probably be a lot of time, more time than I had as a fellow. And then the second way was to do some kind of automated data extraction. So I made friends with the folks who kind of do automated extraction for billing purposes, and they were able to supply me with a data set, essentially in Excel, and then I use that Excel database and a couple of Excel formulas in order to merge the data and then kind of clean it. So hang on, that's a duplicate slide. And so we started with 9,000 patients. About half of those had some kind of biometry. About half of those had the SN60WF lens because I just wanted to restrict it to one lens.
John, may I ask a question?
Oh, yes.
How does the database include the actual biometry data?
Oh, so there's a couple ways to do this. You can extract it from the machine itself. So for example, you can go to the IOL master or the LensStar and you can extract the data. But this actually is not very easy because I think that the manufacturers have not really looked into kind of data dumping. So I think I got really lucky because at Mass Eye, the data was inputted by a human being into Higsoft, which is that IOL calculation platform. And so they have a very, very easy way to export the biometry data. So that was just a stroke of luck, because if I had to extract the data manually from LensStar or from IOL Master, I think it would have been a lot more challenging. I think I would have had to write some code in order to do that. So finally, I was left with about 1,400 patients who met the criteria of having this lens with a 20/25 plus refraction. And I thought that was important in order to ensure that it was an accurate refraction. Now, I can't really check the quality of the refraction. I don't know if the numbers are accurate, but this was kind of the first filter. So I put in the biometry data, and you can see that included things that were not part of traditional data sets or IOL power formulas like sex and age. I didn't know if these would play a role, but since I had the data, I put them in anyway. And essentially, I split the data into a couple sets. I had 100 patients in my test data set, 412 in my validation, and 961 in my training set. So the idea in machine learning is that you want to hold a data set that the algorithm has never seen. So that was my test data set. Then you split the remainder, and 70/30 is a very popular split, into a training set and a validation set. The training set is used to essentially train the algorithm, and it's validated on the validation set. But then once all of that's done, then you expose it to the complete a naive data set, the test data set. So this was my computer station where I ran all of this. Down here was my very fast PC. In Boston winters, it was actually a plus to have this very hot and loud computer. Maybe not the loud part, but very nice heater underneath my desk. And so we can see that over time on the bottom here are the training epochs, and these are kind of the iterations of the neural network. On the left-hand side are the mean absolute error, how close the formula came to the ground truth, which is the postoperative manifest refraction. So you can see that over about 50,000 to 100,000 epochs, the formula became fairly accurate. And it really took around 10,000 epochs to reach a fairly decent point. And you can see here, this is predicted lens power versus actual lens power with a good R-squared value. And finally, I compared it to other formulas that were published. And this is something I'll talk about later in the presentation as well. But you can see here that the neural network was pretty good with a good p-value versus Hoffer-Q, Holiday 1, and SRKT. And you can see here that on-target performance was also quite good. Neural network at 85 and 97% versus the Hoffer-Q, Holiday 1, and SRKT. P-value was also significant. But I asked myself, is this really a fair comparison? It really isn't fair to compare this versus formulas that were developed in the 90s. And so I ran the Barrett, and although the mean error versus the Barrett was significant, the mean absolute error was not. And again, on target performance, you can see the Barrett is now added. It's not inferior to the Barrett, but at 100 patients in my test data set, it wasn't significantly better. If the test data set were extrapolated to 1,000 patients, though, and these results still held true, then I think it would reach significance. But the problem is that my data set was limited. Just as another teaser tool I'll talk about later, I think that we just need to expand these data sets so that we can develop better algorithms. So what we're doing currently with this neural network is that I have a medical student here at UCLA who's a Stanford CS graduate who decided not to go into a lucrative, cushy job at Google, and she's working with me to try to improve the formula. The funny thing that happened was I thought that her initial effort would be way better than what I'd achieved just kind of doing a rudimentary formula, but she actually got around the same as where I got, which shows that these tool sets, meaning the tools that are provided by Google to develop the formulas, are already pretty good and pretty accessible. So at least in this one instance, it seemed like there wasn't a lot of specialty knowledge that could be brought in, even by a CS major from Stanford who had done a lot of machine learning. But certainly for more complex problems, I think that this kind of expertise would really blow anything that I could make out of the water. So what we're currently doing is we're trying to have the formula calculate risk score of being off target. So we're trying to first figure out global averages and standard deviations for every single parameter in the biometry data, and then calculate how far off from the global averages our data is, each individual case, and then try to create a risk score to know when for the formula to predict that the formula would be off target. So the formula is somewhat self-aware. It knows when it's going to spit out a result that's not very confident in. Secondly, we're doing hyperparameter tuning. This means that we created an arbitrary neural network structure. It has one input node and then 2 layers of 10 nodes and then 1 output node. But we really want to see if there's other structures that work better. So essentially, we tell the computer, hey, try to improve on your own results by doing whatever you want to the structure. That's hyperparameter tuning. And finally, what I'm going to talk with you next is scaling the database size. So the EyeData initiative. So this is something that I am trying to get launched, and I'm actually hoping to get help from you guys. So this is at geteyedata.com, currently online, but there's not much on it. You can see this is the entire webpage. But my goal is actually to work with others in the field to create a high quality public data set to host de-identified IOL data. And so the thought here is, remember I showed you that I have about 1,400 good eyes. Austin has 1,000 or 2,000 good eyes as well. If we combine our data sets, we certainly would have a formula that by my prior calculations should be significantly better than the formulas, at least the Barrett. I don't know versus the Kane or versus Hill RBF, but everyone in ophthalmology has their data silo. So Kane has his data, Jack Holiday has his data, Doug Koch has his data. So it would be really, but the problem with all these little data silos is that we don't have the ability to pool those resources together in order to train an AI algorithm. And the second problem is there's a problem of trust. And what I mean is that if, for example, Austin released a new lens power formula tomorrow, it would take a while for the community to adopt it because we wouldn't know how accurate it is. He could publish on his data set, but I wouldn't know for my patients or in a data set that I knew how accurate his formula was. What if we had a data set with 10,000 eyes or 100,000 eyes or 1,000,000 eyes, and that data set was public? And so when Austin developed a new formula, he could say, on this public data set, my performance is this. And then I could say, oh, I know the performance of existing formulas on that existing data set, on that same data set. So thus, I know that Austin's formula is superior. So those are the comparisons that we cannot make right now because all of this data is fairly siloed and it's fairly private. So that's why I think that it would be really great to have a public data set. So it would be for lens formula development. The second thing I think it'd be really cool for is to recruit help from outside of ophthalmology. If anyone's heard of a website called Kaggle, Kaggle, this is a website, if you go on it, where you'll find competitions in machine learning based off of data sets that are supplied by companies. So, for example, this is where Netflix famously held their $1 million prize competition in order to try to have the public create a better algorithm to recommend movies. And the same thing happens with tons of companies now. So a mining company may say, hey, I have this data set of ground scan, sorry, I don't know what data they have, but ultrasonic ground scan data, whatever they use to survey the ground to look for oil. And they'll say, I have this data set and we know the ground truth. We know which sites actually resulted in oil. So how can you guys match up this data? And we'll give $1 million to the highest accuracy or the best solution. So if we have a good public data set, we then could recruit help from outside of ophthalmology. We just give a programmer the data and we allow them to run wild with it and then see where they go. And it could be something that's prize-based. It could be something that's not. But this would allow us to start doing these kind of things. As I spoke to earlier, we want to increase or accelerate the adoption of trust. And finally, we could do some regional fine-tuning. We could take data from that data set and then filter it down to our particular region or ethnicity or whatever we're looking for, and hopefully have, because the data set's so large, more eyes specifically for whatever patient is sitting in front of us to kind of customize our treatment. It's unknown whether or not this would make a huge difference, but this is something we could explore if we had a large data set. So maybe before I switch gears here and talk about human intelligence, does anyone have any questions?
Yes. So Sean, a few questions came in from the chat. I'll see if I can summarize them or at least go through them. So from Dr. Ostreicher, so your data was presumably from multiple surgeons.
Right.
How do you feel about, just that? Because obviously when you collect the data, it's going to be from even more surgeons.
Indeed. I think it reflects the real world. It probably would be a little bit cleaner if it were 10,000 eyes from one surgeon. So that would probably make the formula a little bit more accurate. But I don't know. I guess the answer is also that I don't know what the impact of that would be.
I mean, I suspect that most cataract surgeons are performing very similar surgery nowadays, and most can make a suitably sized rexus and so forth. I don't know how we prevent, data that's, polluted by, but I think it's unlikely there are too many surgeons that are doing something all that different. There was a lot of fuss years ago about everybody should have unique astigmatic adjustments and so forth, but it's just really hard to imagine that people's wounds that are small are varying that much. Another question from the audience was, your data was non-inferior to Barrett, but he had presumably a much larger data set. Did you have any information about how your set might perform for eyes at the more extreme ends of the spectrum?
So that's a great question. we don't have a lot of eyes in the data set at the very, very extremes, but there were a couple eyes that were very far off. And some of those eyes, I debate whether or not to keep those in the data set or to take them out. And I think at small data set sizes, it may throw off the formula too much. But obviously, if you had more eyes, though, you could build analyses at those extremes.
And then this is sort of a very open-ended question, but what else do you foresee AI being used for in ophthalmology besides IOL calculations?
I think our friends in glaucoma and retina are probably ahead of us in utilizing AI for ophthalmology. And so I think that they're doing a lot of really unique work. We were talking about some work done in retina to discover systemic conditions. And so I think that's really big. And then in glaucoma as well. But I think every niche of ophthalmology has some application for AI. One of my colleagues here at UCLA is using facial photos to look for thyroid eye disease, to also detect ptosis, things like this. And perhaps these things can be distributed to apps that reside on people's phones so that these kind of screenings can be done for a number of conditions.
John, I've got a question. Sean, do you what about like the real problems in biometry besides just the axial length, post-refractive, for example? Can you use this to get better accuracy in that cohort of the more complicated biometry patients?
Oh, sure.
That's number one. And the second question, do you need large data, or can you also apply this to more esoteric areas would have a lot smaller amounts of data?
Yeah, that's a great question. Yeah, I certainly think that you could apply this to any type of data set or any type of question you're asking. And the real limitation is just having enough eyes of that type. And so that's why a large data set, if you had 20, 30,000 eyes, perhaps 1,000 or 2,000 would be post-LASIK. And in terms of can you apply it to smaller data sets, this is an area of study in the AI field. Can you train an algorithm to do something else like ImageNet recognition and then use the existing structure of the algorithm as kind of a head start to then fine tune on a small data set? Actually, John Modis is working on this. He's trying to solve the problem of training data on training an algorithm on biometry data that's currently existing, and then answering the question of what happens if we start to measure something else? What if we have new biometry parameters that we don't have in our current data sets? How do we then use that new data in order to fine tune the existing formula? So for example, let's say that we all of a sudden discover that, like shoe size somehow influences IOL data. That doesn't mean we have to throw away all the formulas that we have. We just need to create some kind of correction for that new parameter that we're adding. So good. So I guess I will keep going. So we're going to switch gears a little bit and talk about efforts to train humans to be more similar to machines in some ways. And then finally, I'll share just some musings on what I think is a role of clinicians, particularly in this AI landscape. So before we do that, this was an interesting experiment that was conducted by a Google employee on their 10% time. So they presented an image like this to the machine learning algorithm that was trained on ImageNet and asked the algorithm to find what pictures, what shapes existed in this image. So this is very similar to the exercise when you are a child and you look for animals or shapes in the clouds. So I will click this button and you will see that these are the things that the algorithm found. So out of that cloud image, these are the things that were kind of interpreted by the algorithm. So here we have some mythical animals, this pig snail. We have a six-eyed hippo bird. We have this dog fish. And my favorite one, the dog tripod. So this is kind of funny, but also kind of a lesson in overfitting. Sometimes there's nothing there, right? Sometimes there's nothing there but clouds. But an algorithm can find things there if you ask it to and you give it enough time. So this is a problem, a warning about overfitting. And then this is just another one. You can see here, we just start with a picture of a tree in a field, and the algorithm finds all these other kind of unique features from simply a tree in the field, which is inaccurate. So these are things that we have to be careful about when we're doing machine learning or trying to fit formulas to data sets. So let's talk about the battle for humanity. What do we humans do in the landscape of AI? So this is one effort that I started actually as a resident, this website called iGuru. And I've actually started to develop some tools on this website that are inspired by my work in machine learning. So we have some reach now, and our mission is to organize the world's information in ophthalmology for trainees. If this sounds familiar, it's because we stole this from Google. And essentially, there's a couple of us on the team, myself, my little brother, who's a first-year resident at Bascom Palmer, and David Shu, who's now Will's retina attending. And initially, since I'm telling backstories today, the way we got started with this is we just wanted to make a blog for our first-year residents. And so we just started writing some articles, putting them online. And initially, we had this funny article that we thought, I don't know if you guys are aware, when you click on a link that goes to Amazon, the person who sent you to that link on Amazon, they have a referral program where they get 6% of whatever you buy in the next 24 hours. So that's why there's so many websites online. If you type in like review of camera lenses, you'll find a billion websites about camera lenses because that's a very high value item that people can then link to on Amazon and then get a referral fee. So this is a very, very smart marketing strategy by Amazon. So we made this ultimate callback guide to refer people to things on Amazon, thinking, hey, this would help pay for hosting and things like that. And so in this article, we talk about things like messenger bags and depressors and Q-tips, very, very low value items, unfortunately. In all of 2018, we made $82. And you can see it's right around July when people are looking for things to put in their callback. So I can't say this was a smash success. Our hosting is well over that every single month, but it doesn't hurt. It doesn't hurt. So anyway, that's how we got started. We just had a blog. And then I thought, when we train machines, we essentially just feed machines tons and tons of images in rapid succession, telling the machine what is correct and what is not. Why couldn't we do the same thing with human beings? So we essentially built these things we call mastery trainers, where we take 100 images of OCTs or 100 images of fundus photos or 100, and we recently developed our topography module. And we have experts annotate these images. So it's as if you were getting somebody, an attending's opinion in clinic. And then we have trainees use these modules in order to go through and learn how to do pattern recognition for various diseases. So on the website, we compare it to clinical learning. And seeing 100 images in clinic may take a couple of days, depending on what kind of clinic you are. The feedback is inconsistent at times. There's no annotations. And clinic is often busy. We're just trying to get through the day. We're just trying to survive. And so it's hard to do teaching in that context. On the other hand, you have books, which are not interactive. And often there's just one image of a particular disease, that one classic image. So what we're trying to do is to create a new way to train trainees to perform pattern recognition. So it may only take you an hour to see 100 images and get expert feedback. And you can see multiple disease examples, not just the classic image in that sphere, but a range of things from classic to a little bit more kind of esoteric, and you can learn anywhere. So this is what we're trying to do with the Mastery Trainer. This is all, of course, free. Everything on iGuru is free forever. That's our goal. We're just trying to make tools that we would want to use in residency. So you can see we have imaging modules, and we have the OCT ones online. We just put our topography one online. We have a fundus one, and then we're doing visual fields right now. So finally, I want to end with this. There are so many companies in AI, and every single day, if you open the news or look at your phone, you'll find another company doing something really awesome in this space. And it's easy to feel kind of left out as clinicians. It's easy to feel like, what is my role in this? Am I going to be replaced? This is a question that people ask me a lot. And I unfortunately think the answer is that I will not be doing surgery by the end of my career. In the next 20 or 30 years, I'm pretty certain that a machine will replace what I do. So then the question is, what is our role as clinicians in this landscape? So in medical school, I took this class called biodesign, And in this class, an MD, an engineer, my animation ran a little quick, an MD, an engineer, and MBA were put together on a team. So let's put these folks here in the corner. And I'm going to go through just one of my thought processes on what our role is in this kind of new landscape. So the idea comes from somewhere. And in this first step of ideation, only we as clinicians know what our needs are. We see patients every single day, and we have a good sense of where our pain points are and what we would like to build. So that's why I put the MD here squarely in charge of this process, so to speak. Step 2 is we have to get data. So in order for us to get data, which is very heavily protected in the US, and I'm sure in Canada as well, it often takes a physician champion. So Google can't just come to UCLA and say, hey, give me all of your biometry data. They have to come through somebody, hopefully like me or somebody else who's a clinician here, because we are the ones who have the connections and can explain to the organization why we should work with whatever particular partner is coming to us. But also I put the CS icon here, but because the computer scientists are ones who can help us clean the data and help us get the data ready for the machine learning algorithms. Third, I have kind of goal setting and vision setting. This is also squarely in the realm of clinicians, because we are the ones who know what we want. We're the ones who can figure out what the end result of the work should be. Fourth, coding. So I alluded to earlier that you could learn machine learning in about 10 to 11 hours. But ultimately, the people who do this full time are going to be better than us, especially as the problems get more and more complex. But at the same time, I think it's important for us to invest those couple of hours learning the basics of what can and cannot be done with artificial intelligence. I think it's really, really time well spent. So I put in charge of this process, CS, but with kind of input from the MD. Then we have an idea, we have an algorithm, now we're going to market. So here's where we hook up with VCs and private equity and institutional investors, and we try to pitch our product, get funding, and then expand and accelerate our efforts. So here the MBA can help us do market analysis and do fundraising. But oftentimes on these teams, they want to know, what is the clinical relevance? Do doctors care about these problems they're trying to solve? And so I think that clinicians are very, very involved in this step as well. It's very, very important to have a clinician on your team in order to help do these pitches. Then we need to integrate these processes into, or these algorithms into clinical processes. Right? We have this beautiful algorithm, let's say it's just a website online that does IOL calculations. How do we get clinicians to use that? It's very, very hard for somebody to change the process of what they're doing. So it's very unlikely that if I put up a website with my formula that anyone's really going to use it. Most likely what has to happen is that we need to integrate that algorithm back into clinical processes. We need to license that technology to Lenstar or to IOL Master, or Zeiss, I mean. So we need to get that into the clinical kind of flow that clinicians are already used to. So this also involves the MD. Then we have to sell it. We have to, this company has to make some money to survive. So we need MDs as key opinion leaders to talk to other MDs, because who do we trust more than one another? So this is also a role for MDs to be involved in this process. And finally, iteration. We've made the formula, it's integrated into clinical processes. Now we need to gather feedback and we need to make things better. And so this is also a process led by clinicians, because clinicians need to tell the company how to improve the process and what the new pain points are now that the algorithm is developed. So this is just one way to look at what we do. And you can see that MDs are involved in every single step of this journey. And I think MDs are the crucial aspect and the crucial ingredient in all these steps. And finally, I'll speak on my last slide to the art of medicine and how I think we fit into this landscape, just another framework. So machine learning, we take inputs and we have outputs. And in between, we have nodes. And so then we connect these nodes and inputs and outputs in order to create our final result. But the inputs don't come from nowhere. As I was talking about in the last slide, I believe there's a cognition layer where you take curiosity and creativity and invention and you connect that to create the inputs. And the outputs, we need to do something with them. So here's what I think is the application layer, where we have empathy and goals and needs. And so we need to connect what we make to these very, very human elements. And then once we have that, then we can help patients and organizations and the world. And then we connect back to iterating on our solution. So at the end of the day, the take-home points are that we have these advances of AI driven by techniques and computational power and data capture, and we can solve these problems with high accuracy. But I think that we do play an indispensable role in this process. I guess I'll add for now. Okay, that's all I have. Thank you.
That was fantastic, Sean. Thank you.
Any questions? Is this QR code okay? I just kind of put it on.
Yeah, I'm just playing with it to see if it works there. I got it to work. Yeah.
Okay, good.
Okay, good.
John, can I ask a question to get the ball rolling, maybe?
Sure.
First of all, congratulations. I thought that was an outstanding talk, and this is really sort of a glimpse into the future. Clearly, the landscape is changing. What do you advise? Given especially your last slide, what should we be telling new residents, new medical students about their roles over the next decade or whatever? What's our advice to medical students who are just starting or to residents who are just starting?
Thank you for the question. I thought a little bit about this as the associate program director. What do I do to prepare my incoming residents for this new landscape? And so I can't force people to learn how to code. I think that what I'll be doing is I'll be offering a mentored project with whoever wants to work with me to take my existing data set and go through the process of learning how to do AI. Just doing that basic programming, learning data through DataCamp, and learning just the basics of doing this. Because I think they could complete it in a reasonably short amount of time, somewhere 10 hours spread over 1 or 2 years. And I think they would gain a lot by learning this process. So that's what I think initially, for some people, they may be interested in. For others who aren't interested in coding, perhaps this lecture or others can spark their interest in thinking about what their role might be. So those are the kind of two directions that I initially thought that we could take residents, from kind of very high involvement to more kind of lower involvement, but still understanding the process.
So Sean, there's been a couple of very large papers. There was the Mellis paper out of California, and there's a big UK paper from the NHS. Are these folks willing to let you run your formula on their data? Have you approached them? Are they, because I see that those authors have, or can you give them your formula? Because I see they ran Evo and Kane on their data sets.
Right. So I think that we're kind of in the infancy of trying to figure out how to run different formulas on different people's data sets. So what my goal is not necessarily to make my formula the best, because I think that there are people who are doing this better than I am. My goal is to try to organize the data in such a way that it becomes easy for other people to develop formulas and to test their formulas. So one of my initial goals, if you see on Get EyeData, is to give this data, and hopefully they would reciprocate by sharing some of their data as well. It doesn't have to be the entire data set, but parts of their data set that they would feel comfortable sharing. And so even if a small number of clinicians share a small amount of data, it would be more data than we've ever had access to. So that's kind of where I'm going with this.
And I guess for the residents, recency bias, we have our optics exam in a couple of minutes, and we learned about the SRK formula, how there's a 2.5 diopter impact for every 1 millimeter change of axial length. But now we have all these new biometric parameters like lens thickness, for example. Just curious, in your model, was there a particular biometric parameter that had a bigger impact or weight on the results of your predictions?
It's a good question. It's a challenging one because oftentimes these formulas are black boxes, and it's hard to see into the workings, understand what the weights are. So that's actually one of the biggest questions of AI. How do we look behind the curtain? So I can't offer you any advice there.
Thanks.
And just a couple of other questions that I actually never had thought of. One attendee asked about what are the consent issues for patients providing this data? Just like we know Facebook is mining our data and so forth. I've always assumed because it's anonymized, there are no issues that way, but maybe you had to think about that yourself.
Yeah, this is actually still in progress because I'm working with Matt Sioneer and Dr. Roberto Pineda to try to look through some of these things. And some of these issues currently, especially for de-identified data, don't have any strong precedents of how we treat this. So I think for me, as I'm collecting new data in my clinic, I'm starting with kind of a blanket consent that they sign as just the first measure so that we can use de-identified data in the future. But even here at UCLA, as I was asking around who even gives me permission to collect this or to use this, nobody really knows. It's a little bit uncharted territory.
So Sean, there's a question here from Dr. Ostreicher. What do you mean by clean the data, and does that bias the accuracy?
Sure, that's a great question. What I mean by clean the data is, for example, in an operative report, it's just written in free text based on a template. So initially, when I was going through the data, I tried to write an algorithm to pull out the lens power and the lens model. But I found that this was very challenging because if somebody wrote other numerical data, such as a serial number or the axis of astigmatic incisions, this would often get pulled out instead of what I actually wanted. And I needed that step to be a very, very high accuracy. I needed essentially to be 100% accurate because if I had a value of 1 for the lens power when it was actually 20, that would throw out the formula significantly. So cleaning the data in an intelligent and efficient way is very important. So what I ended up doing is realizing that it wasn't completely a machine-driven process that would be optimal. It was a combination of human and machine processes. So for example, what I did is I had the formula just pick out the region of the operative report that was a lens power formula. And then I would manually process the actual numbers. So I made sure that it was always accurate every single time. So that's just one example of cleaning the data. Sometimes it's not always best to have the machine do it because you need that process to be highly accurate. But yet you don't want to read through the whole op report. So it's best to have a hybrid approach at times to filter the data so that you as a human can then make that final judgment. So those are kind of steps involved in cleaning the data. Now, does that introduce bias? I think that in my formula, the steps I was using to clean may not. But am I introducing bias by excluding eyes that were worse in 2025? Perhaps, because maybe those eyes have some influence on making the formula better. But at the same time, I on the initial foray, I wanted to have as clean of data as possible, and I wanted to exclude comorbidities.
Another interesting question here, which is actually kind of fascinating from Wendy Hatch. So we know, you talked about that presentation where the fundus photo can tell you the patient's age, gender, smoking status. Can there come a time where the machine can actually identify an individual person based on some photo that you've given it? And then maybe coming back to the consent issue, do we need to consent for these types of things now for what the machine can do in the future?
I'm sure there will become a time because as ubiquitous as blood pressure cuffs are in pharmacies, there are a lot of companies working on fundus cameras to detect DR and glaucoma. And so at that point, we'll have, and imagine if every single human goes to a pharmacy at some point and gets their fundus captured, then all those humans are in a database. And at that point, pretty much, I think there would be a very, very, unfortunately, easy way to be able to identify humans based on fundus photos. So I think that those are the legal and ethical issues that have not really been worked out yet. And so this is a really, really great area of research as well, the ethics of doing all of this. I think it'll start with consents, but I think we're going to realize eventually that we're going to need better processes around this because the fidelity of recognition will be very, very high.
Another question from the audience was, have you considered doing a parallel run of the data on eyes less than 2025? That data is there for you to run if you choose to.
Yes, so I would just answer by saying I will make the data set available. I have not done the run yet, but it will be up to one of you to run that data.
Oh, hi,
And
Dr. Lynn. Oh, sorry.
no, you go ahead.
Oh, thanks, Dr. Lloyd. Just wanted to say I really enjoyed your talk, Dr. Lynn. I was just wondering about the database that you're trying to make and what sort of data you'd be trying to collect. The sort of AI work I was doing is usually using fundus images, like sort of what you mentioned earlier. And most of the work has been based on publicly available images that are collected from other institutions. But I think one of the benefits of making your own database is you know and are able to trust the data that you have in it. And also if it's collected from multiple institutions together, then we can all test our different algorithms on the same data set. So I just wondered what sort of data you're hoping to collect.
Thank you. That's a great segue. So I'm actually looking for other institutions to contribute to this data set. But I think we probably all have questions that we have to answer within our institutions related to data fidelity and also related to sharing of data even in a de-identified way at this time. So I'm just looking to collect right now biometry data from whatever machine that you have biometry data for. So I know, Austin, yours is Iowa Master 500. The majority of my data set here is Lenstar, but what I would do is just collect all the data. We list it by institution, list it by the author who provided it, and then also just kind of catalog what data is included in that particular part of the data set. And so then the combined data set, whether it's through Excel or however we share the data, would be filterable by those parameters. And somebody could say, I just want to build a formula on axial length, keratometry, and ACD. And so maybe they could use a whole data set. But if they need more specific things like white to white or lens thickness, perhaps they need, it's a smaller portion of that data set. So I'm basically taking any data right now, but in the filters will allow you to be able to filter it by what you need. So maybe Austin and John, maybe we can continue this conversation offline about how to make this happen.
Well, Sean, I find this absolutely fascinating, and I really hope that you've inspired my residents who are going to carry the torch in this field. There was a time I was a computer geek, and I think that time is drawing to a close. But it's really inspiring to see what cryptocurrency has now done for ophthalmology here with your work. So thank you very much for presenting to us. Thank you especially much for getting up at the crack of dawn here. I hope you have a little nap before you got to see your patient load today. Maybe your robot can do your surgery for you. And